Good morning, everyone. This class we will focus on electric fields and forces. And then next class we talk about forces, charges, and some Coulomb's law. Yeah, using Coulomb's law to calculate the force. Yeah, between two different objects or two different charges. Yeah. Today we will focus on like electrical fields and forces. Okay, let me share my. Okay. Uh, yeah. Uh, last class we talk about what's the goal for chapter 20. Yeah, actually, in this chapter, we mainly focus on to develop a basic understanding of electric phenomena in terms of charges, forces, and fields. Yeah, and in last class we talk about charges and forces. In this class, we mainly focus on fields. Yeah, let's continue. Yeah, this is today's goal. Firstly, we will review Coulomb's law, and then we try to understand the concept of the electric field. And next, we will explore the electric field of multiple charges, and then we examine conductors and electric fields. Yeah, finally, we will study forces and torques in electric fields. Yeah, this is what we will learn in this class. Yeah, a lot, am I right? So let's continue. Uh, yeah, we learn Coulomb's law like in last class, and let's review it. And yeah, we talk about the forces between two charged particles Q1 and Q2 separated by distance r. uh, r. We can define the forces between two charged particles using these equations. Yeah, actually the Q1 on Q2 or Q2 on Q1 is the same thing, because you can see here it is the absolute symbol, and the magnitude is the same, but just the direction, you can see the direction is different. Yeah, and here k is a constant. Yeah, uh, it should be, oh yeah, like a key, you can use this one or this one. Yeah, it is the same thing. It's a electrostatic constant. Yeah, this constant value is fixed. If you calculate the force, you just use this. Yeah. Okay, and for the Coulomb's law, these forces are an action or reaction pair directed along the line joining the particles. The forces, yeah, the forces are repulsive for two like charges, the one is positive, the other is positive, or one is negative, the other is negative. Those kind of particles we call it, those kind of charges we call it like charges. And attractive for two opposite charges, which means one is positive, the other is negative. Yeah, this is opposite charges. The net force on a charge is the vector sum of the forces from all other charges. You can see here. If we want to calculate the force on this charge, and there are different charges, and if you want to calculate the different charges to this one, and you just calculate the all, and then use the vector. This is vector sum to sum those all, and then get the net force. Okay, the unit of charge is a Coulomb, and short for C. Yeah. Okay, this is Coulomb's law. Yeah, I hope you can remember these things and know how to calculate it. And let's continue. Yeah. In today's class, firstly we will talk about the concept of the electric field. Yeah, there are some per lecture video like electric fields. I think there are some like quizzes, reading quizzes. You will see these videos. If there is no these videos, you can review these videos using this link. I will now play the videos here. And okay, let's talk about the conception of the electric field. Yeah, the field model explains how the force due to charges is transmitted through empty space from one charge to another. Yeah, this figure shows a shallow pan of oil with grass seeds floating on it. When positive and negative wires touch the oil, yeah, you can see here, there is a positive, there is a negative charge, like wires touch the oil. A pattern emerges. Yeah, there you can see there is a pattern. Yeah, did you see that? Yeah, so, some kind of electric influence from the charges fills the space around the charges. Yeah, you can also like see a video to see like visualizing the electric fields. Yeah, we will not play this here. Okay, let's continue. Yeah, in the force model of the electric field, the positive charge A exerts an attractive force on charge B. Yeah, you can see this is a positive charge and this is negative charge. And the positive charge A exerts an attractive force on charge B. Yeah, and then in the field model, it is the alteration like of space around charge A that is an agent that exerts a force on charge B. Yeah, you can see like the alteration of a space is what we call a field. Yeah, the alteration of the space, you can see, we call it a field. The charge makes an alteration everywhere in space. Space, you can see in the field mode. Yeah, A alters the space around it. Yeah, the wavelengths are Portic license. We will soon learn a better representation. Yeah, we will. There will be a better representation later. And the particle B then responds to the altered space. The altered space is the agent that exerts the force on B. Yeah, you can see. You will sometimes you will like you will have the question A and B. They didn't touch. Yeah, they have the space, but they have the force like electric force. How can they do this? Yeah, actually they just use like you can see even B is and A has a distance, but A will like exerts like there it orders the space around it. Yeah, and like this altered space B in it, and then it will like the particle B then responds to the outer space, and then the force came out. Yeah, does it make sense to you? Okay, and the space around a charge is altered to create an electric field. Yeah, you can the space around a charge is altered to create an electric field. The alteration of space around a mass is called the gravitational field. Yeah, like around a mass. Yeah, a gravitational field. The alteration of space around a magnet is called the magnetic field. Yeah, we will talk about this later in other class. Yeah. Okay. Yeah, the field model is very useful too for visualizing and calculating forces for complex arrangements of charges. Yeah, actually, we talk about some like calculate forces like using Coulomb's law. Yeah, but you can see what we calculate is very easy, just a two charge or some, or like maybe like a three or four. But you know, in the real world, it's very complex. Yeah, so like the field model is very useful tool for us to like calculate forces for complex arrangements of charges. Yeah, but the electric field is real. Yeah, you can see in the real world, you cannot see the electric field. Am I right? Yeah, but it is real. It exists. It not just an abstraction. Yeah, it's just not like for example, the idea, for example, some dream. It's not like abstract abstraction. It's real. Yeah, to many creatures, the electric field is certainly not an abstraction. They actively sense the electric fields in their vicinity and use them to navigate, locate prey, and determine the best flowers to visit. Do you remember this picture? Eh? Oh, sorry. Oh, yeah, this picture. Yeah, actually, you can see. Yeah, in this picture, like this being, actually they can sense the electric fields in their vicinity and use these to navigate. Yeah, the beings can use these like electric fields to navigate, locate prey, and determine the best flower to visit. Yeah, that's the reason why uh, I put this image here. Yeah. Okay. So, let's continue. Towards the end of our study of electricity and magnetism, we will explore electromagnetic waves of electric and magnetic fields that carry energy and information through space. Yeah. Okay. Yeah, like let's talk about the field model. Yeah, the field model describes how charges interact. Yeah, a group of charges, which we will call the source charges. Yeah, alters the space around them by creating an electrical field. We using this to represent this electrical field. If another charge is then placed in this electrical field, it experiences a force. Yeah, of course, exerted by the field. Yeah, does make sense to you? Yeah, when there are some like source charges form an electrical field, and if you put another charge in this electrical field, this charge will experience a force, yeah, exerted by the field. Yeah, that makes sense to you. Okay, there is also a video, you can check it later. Okay, yeah, we define the electric field at the point, you know, like it field is just like a space. So you will see there are three different dimensional. Yeah, as yeah, we can define the electric field using these equations. The E at XYZ equal like this is force on Q at this point, and divide the charge. Yeah, electric field at a point defined by the force on charge Q. The units are newtons per coulomb. Yeah, because yeah, and the magnitude E of the electric field is called the electrical field strength. Yeah, that makes sense to you. Yeah, this the magnitude E is we call it electrical field strength, and the direction is yeah electrical field direction. Okay, there are some typical electric field strengths. Yeah, you can see here inside a current carrying wheel. Yeah, the field strength is this one, and the earth field near the earth surface. You can see, yeah, if you know like if you know that yeah our earth is also like a big chart like that, yeah, and this is our earth field, and near objects charged by Robin, yeah, this is field strength, and needed to cause a spark in air, you need to use this field strength inside a cell membrane. Yeah, this one inside an atom. Yeah, this. Yeah, it's pretty big, right? So which means you can see many things. You can see our many objects are from from atom, yeah, and this atom, like inside the atom, the field strength is very huge, which means it is difficult to break. Yeah, that makes sense to you. Okay. Let's continue. Yeah, you can use charge Q as a probe to determine whether an electric field is present at a point in space. If charge Q experiences an electric force at that point, then there is an electric field at that point causing the force. You can see here, charge Q. Yeah, this is one charge, this is the other one. One charge. Charge Q is placed at two different points in space. The force on the charge tell us that there is an electric field at this point. You can see if there is no electric field, there will not be a force on like this charge. But there is a force on this charge, which means there is a there is an electric field. Does it make sense to you? Okay. The electric field vector defines the electric field at a point where a charge experiences an electric force. And you can see, yeah, this is the electric field vector at point 1. Yeah, this is the electric field vector at point 2. Yeah, the dots are the points at which the field is known. Yeah, like the points. Yeah, does it make sense to you? Yeah, the electric field vector like defines the electric field at a point where a charge experiences electric force. Yeah. In the field model, the field is the agent that exerts an electric force on a particle with charge Q. Yeah, the electric field, a vector, exists at very point in space. Electric field diagrams will show a sample of vectors, but there is an electric field vector at every point, whether one is showing or not. Yeah. If the probe charge Q is positive, the electric field vector points in the same direction as the force on the charge. If negative, the electric field vector points opposite the force. Yeah, this is the definition for the. Yeah, if the probe charge is positive, yeah, the electric field vector points in the same direction as the force on the charge. If negative, the electric field vector points opposite the force. Yeah, the electric field is independent of the charge Q used to probe the field. Actually, you can see if you don't put this charge, and the electric field is always there, so it is independent of the charge Q. Yeah, the electric field depends only on the source charges that create the field. Yeah, only depend on the source charges. For example, our Earth, no matter you put how many like charges in your area around you, yeah, the Earth, the electric field of our Earth is not changed. Yeah, doesn't make sense to you. It's only like depend on the source charges. Yeah. And a point source charge Q creates an electric field at all points. Yeah, you can see. Yeah, a point source like a charge Q creates an electric field at all points. Yeah, you can. Yeah, even like a point source charge can create an electric field. Yeah, we will use a second charge Q dot to probe the electric field. You can see here. Yeah, we want to. Yeah, there is a point charge Q, and then there will be a question, what is the electric field of Q at this point? Yeah, we just put a second one, Q dot. Yeah, if both charges are positive, the force on Q is given by Coulomb's law. Yeah, we know the Coulomb's law, and then we can calculate the force. Yeah, using this equation. Yeah, since these two like both are positive, so the force will be away from Q. Does it make sense to you? Okay. And yeah, the electric field is defined as using this equation. Yeah, like E equal F divided Q dots. Yeah, because we talk about the equation just now. Yeah, this equation. Yeah, the force at that point divide the charge. So for the Q dot, yeah, and we know this is a force on Q dot, and this is a charge Q dot. So like the for the positive charge Q, the electric field is using this equation, yeah, away from Q. Yeah, because we talk about this, like if yeah, if like if the charge is positive, the electric field vector like is the same direction as the force on the charge. If it is negative, and it will like opposite the force. Yeah. Okay, so like yeah, so the the electric force is this direction. So the electric field is also this direction. Yeah, and the magnitude you can get from this equation. Does it make sense to you? Okay, let me talk about why the electric electrical fields is this can be represented in this equation. You can see here the electric force equal this one. Yeah, so we just write it here like E, and then we will have E equal force Q equal what? Equal like K Q dot. This is force, and then Q dot. All right. So which means that the Q dot can be removed, and then this one will equal Q. Does it make sense to you? Yeah. So we can use this equation to represent the electric field, and then you can see since like this one is positive. We know that. Yeah, the prob and we talk about the prob charge if it is positive, and the electric field vector like points in the same direction as the force charge. Yeah, so yeah, this is the point. This is positive. This is positive. So the force is it's in this the force direction in this direction in this one. So the electric field is also to this one. Yeah, to this direction. Does it make sense to you? Okay. And if Q is negative, the magnitude of the force on the probe charge is the same as the previous equation. Yeah, you can see if Q for now Q is positive, am I right? But if Q is negative, actually the magnitude, yeah, is the same thing. Yeah, that's the same as in the previous, but the direction is toward Q. Yeah, the direction will goes to this one, because you can see, and this is if Q sorry, if this Q is negative, which means this one is negative, am I right? But the probe, we know it is positive, am I right? Yeah, it is this one here is positive. So which means the force direction is one is negative, one is positive. So the force direction will this direction, and we know like the probe is positive. So the force direction and the electrical field direction is the same thing. So the direction will just like this. Yeah. So for when if that makes sense to you. So when the Q is negative, yeah, the magnitude of the force on the probe charge is the same as in the previous, but the direction is toward Q. It toward to Q. Does it make sense to you? Okay, the general expression for the field is using this equation. Yeah, if like a Q greater than 0, like it is positive. Yeah, and the direction will away from Q. Yeah, just like we talk about it will away from Q. If it is negative, if this Q is negative, if this is negative, and like it will toward the electric field will toward Q, and the magnitude is just using this equation to represent. Does that make sense to you? Yeah. Okay. Let's talk about one example, finding the electric field of a proton. Yeah, the electron in a hydrogen atom orbits the proton at a radius of 0.053 nanometer. What is the electrical field due to the proton at the position of the electron? Yeah. Okay, the proton's charge Q, we know equal E, am I right? And also we know what's E. Yeah, we have a topic in last class. At the distance of electron, the magnitude of the field is using, yeah, we're using this equation. Yeah, using this equation to calculate the electric field magnitude for the electric field. Yeah, Ke, yeah, we know like the proton charge is E, and the R, yeah, here is the distance, yeah, is R. And then we can get the electric field is this value. And because the proton is positive, the electric field is directly away from proton. Yeah, so yeah, and this is the electric field, and all the direction is outward from the proton. Does that make sense to you? Okay, this is the charge field, but table 22 shows that this is the correct magnitude for the field with an atom. Yeah, you can see. Let me show. Yeah, there is a table here. Yeah, you can see here. If you check this table, you will see our result makes sense. Okay. Let's talk about the electrical field of a point charge. Yeah, an electric field diagram for a positive point charge is constructed by drawing electric field vectors at a number of points around the positive charge. And all the vectors point straight away from the positive charge. Yeah, we know that if the if the Q is positive, and it will it will away from Q. It is negative. It will toward Q. Yeah. So here we just draw a electric field diagram of a positive point charge. You can see all the direction will away from this point. Yeah, the field vectors point away from a positive charge. Okay. Yeah, and the electric field diagram for negative charge is drawn with a vector pointing towards the negative point charge. This would be the direction of the force on a positive prop charge. Yeah, you can see here the field vector point toward, yeah, a negative charge. Yeah, just like we talk about. Yeah. For an electric field diagram, the diagram is just a representative sample of electrical field vectors. The field exists at all the other points. A well-drawn diagram gives a good indication of what the field would be like at a neighboring point. The arrow indicates the direction and the strength of the electric field at the point to which it is attached. At the point where the tail of the vector is placed, the length of any vector is significant only relative to the length of other vector. And this is some features for electric field diagram. And yeah, and although we have to draw a vector across the page from one point to another, An electric field vector does not stretch from one point to another. Each vector represents the electric field at one point in a space. Yeah, like this is some features for an electric field diagram. Let's try to check some quick let's try to review some quick check questions. Which of the two sets of electric field vectors is possible? Yeah, here are some source. Yes, so here are some some charts here and here. Yeah, which of the two sets? Which means if it is like a outward, so which means this is positive, this is positive, and this is positive, this is positive. Actually, you're not sure if there is other charges around this one. So actually, and also like the electrical forces field is actually there will be a superposition. You can see it can be crossed. Yeah, so the answer should be, yeah, both A and B are possible. Yeah, if you can see here, if there is another source charge and this one, yeah, this one will be if it is positive and there are other electric field affected, this one and this one will happen. This and this also will happen. That makes sense to you? Okay, let's check the other one. At which point is the electric field stronger? You can see this is the source charge, and this is the electrical field. Yeah, electrical field equal what? Equal KQ divide R square. This R is the distance, am I right? So which means this R is smaller. For A, the R is smaller. For B, the R is bigger. The smaller means the electric field bigger. So which means the answer should be A. That makes sense to you? Yeah, you just use this equation. And let's talk about the other one. Ranking order from largest to smallest, the magnitudes of the electric field at the black dot. Yeah, you can see here. It's a similar thing that we just write the equation here. E equal K Q R. So this one is K Q square. This is K2Q 4. Yeah, plus 2R. Yeah, this is K2Q. This is this is KQ. Yeah, which means the last one should be this one, 3. I'm right, and 3 is the greatest one, and then it should be, yeah, it should be 1. Yeah, because this one is KQ divide R square, and this is KQ divide 2 square. Yeah, so then 2, then 4. Yeah, 4 is the smallest. So which means 3, 1. Yeah, this one, D, is the right answer. Yeah, that makes sense to you? Okay, let's talk about the other one. All charges shown have equal magnitudes. For case 1 through case 2 showing is the electrical field at the dot to right, to left, or 0. Yeah, let's try to see this one. For the case 1 and yeah, for the case 1 and the electric field for the dot, yeah, this is for this positive is just like this, negative is just like this, but this is like a near, so this one should be greater, and then this direction should this one is left, and for this one it's just it's just a bigger, smaller, so this one should be left. Yeah, does it make sense to you? Yeah, and yeah, this is left, this is right, and this is for this one should be this. Yeah, because it will away, and this way should be left. and this one it should be, yeah, it will be 0. Yeah, because this one is equal, and this one is this is outward for this one. This is our yeah. This is sorry. This is yeah in, and this is toward it. This is toward it, and the value is equal. So this is 0. So which means LR 0, which means the B is the right answer. Does it make sense to you? Yeah. Okay, let's talk about the other one. All charges shown have equal magnitudes. Ranking order from largest to smallest, the magnitude of the magnitudes of the electric field at the black dot. Yeah, yeah. Here, this one should be for this one. It should be outward. This one should be in should be inward. So which means and this one should be inward, outward. Yeah, but oh yeah, but this inward. Yeah, which means this one is just a 2 plus, and this one is for the positive, it should be outward. For the negative, it should be like should be inward towards it. So, but this one is bigger, so the total will be this direction, and this is outward, outward. Yeah. So this one is inward, inward. So this one will be 0, and yeah, this one is the smallest one. So, and this one is the greatest one. Yeah, because it is just you know, this one greatest one, because this one and it is 2. Yeah, this one and this one also near, so which means the 1 is the greatest one, and then the 3, and then the 2, and then the 4. So which means the D is the right answer. That makes sense to you? Yeah. Okay, let's talk about the other one, which is the electrical field at the dot. Yeah, here. Here, because the source charge is negative, which means it will point to the point to this one. So the electric field should point to this field. So which means it should be B. Does that make sense to you? Yeah. And let's see the other one. Let's see the other example problem. A small bead sitting at the origin has a charge of this one at the point 3 centimeter, 4 centimeter. What is magnitude and the direction of the electric field due to this bead? So we know like K equal what? No, sorry, okay. We know E equal KQ divided R square. K we know that, and Q is a positive 10 N1, and then the distance of the point from the charge is this one, because this is yeah, at the point what is there is a small bead, so sitting at the original, and the point at a point, this point is in this x 3y4, so which means the distance should yeah, this is 3 4, this is 5, and then r means this r means 5, am I right? So we just using this equation here, this equation to calculate the E. So yeah, since like the it is positive, so the direction is away from the B, and yeah, and this is the magnitude. Does it make sense to you? Okay. And let's talk about the other one. A housefly. Yeah, you can review this problem detailed. If you have any questions, let me know. Yeah, a housefly working across a clean surface can accumulate a significant positive or negative charge. In one experiment, the largest positive charge observed was this one. A typical housefly has a mass of this one. What magnitude and direction of an electrical field would be necessary to levitate a housefly with the maximum charge? Could such a field exist in air? Yeah, we just use E equal what? KQ R. And the electrical force QE would need to exceed. Yeah, actually the electric force would exceed the weight mg. Yeah, equal this one. The E equal using this equation to calculate equal this one. This is about the field strength resulting in discharge through air. So it is unlikely the field would be strong enough to levitate a fly. Yeah, you can see here. Yeah, it's now like strong enough. Yeah, the field would be reduced by a discharge before reaching the strength necessary to levitate the fly. That makes sense to you? Yeah, you can like try to resolve this problem. Yeah, step by step. If you have any question, just let me know. This is just some hints. Okay, let's talk about the section 25, the electric field of multiple charges. Yeah, we have already talked about the electrical field, just a single charges. You can see here, single one. Yeah, this one is a positive, this is negative. And for now, we will talk about the multiple charges. Yeah. Yeah, let's talk about the electrical field of multiple charges. Yeah, no matter the number of source charges, the electric field at a point in space can be found by looking at the force on a probe charge. The electric field due to multiple charges is a vector sum of the electrical field due to each of the charges. Actually, it's similar with the electrical forces. Yeah, for the electrical field, for one point, you just need to calculate the vector sum of the electrical field due to each of the charges. That makes sense to you? Okay. And let's before we talk more, let's talk about one example, finding the field near a dipole. Yeah, a dipole consists of a positive and negative charge separately by 1.2 centimeter. Yeah, you can see here is a positive, here is a negative charge. As shown in this figure, what is the electrical field strength along the line connecting the charge at a point here to the right of the positive charge? Yeah, for these questions, the dipole has no net charge, but it does have a net electrical field. Yeah, you can see this dipole. What is dipole? Do you remember that? Yeah, a dipole usually it consists of one positive and one negative charge, but the same value. Yeah, so these two just form a dipole. Yeah, the dipole has no net charge. Yeah, because the negative and positive is equal, but it does have a net electrical field. Yeah, the electrical field is the sum of the fields from two charges. Yeah, you can see this one it will outward and this one it will inward. Yeah, for here and in this dot and the electrical field come from the positive will be this one, and from the negative will from to this one. Yeah, but this is further, so this one should be smaller. That makes sense to you? Yeah, you can see it's a similar thing we analyze. We define the axis to be along the line connecting the two charges as in the figure. Yeah, this is the axis. The point at which we calculate the field is 1.2 centimeter from the positive charge. Yeah, and 2.4 centimeter from negative charge. Yeah, yeah, because from here to here is 2.4. Yeah, thus the electric field will be larger as shown in the figure. Yeah, the light electric field of the dipole is a vector sum of these two fields. So the electrical field of the dipole at this point is in the positive x direction. That makes sense to you because this one is bigger than this one. Yeah, the magnitudes of the field of the two charges are given by equation 26. So the magnitude of the dipole field is, let me see. Yeah, like the equation 20.6 is just this equation. Let me show you. Yeah, it's just this equation. This equation is 26. I need to label here. Yeah, and yeah, so then we will have yeah, for one like a electric field we can calculate, and for two it's a similar thing. Yeah, just use different equation. You can see here is E positive. Yeah, because this one to this one is 1.2 centimeter, but here to here is 2.4 centimeter, and then you just like for the magnitude it should be minus. So this is the net electrical field. Yeah, that makes sense to you? Okay. Yeah, let's assess this question. Yeah, table 20.2 lists the fields due to objects charged by rubbing as typically 10 typically in this range. Yeah, and you can see this is our result. Yeah, actually you can see it is reasonable, and we've already seen that charges caused by rubbing are in the range of 1 to 10 and see our answer is in the range, and thus it is reasonable. Does it make sense to you? Okay, let's check some like quick. Let's review some quick check question. What is direction of the electrical field at the dot? Yeah, at this dot. Yeah, for the like positive, you can see the it should be outward. For the negative, it should be inward. Yeah, so which means the final direction should this one. So the answer should be D. Does it make sense to you? Yeah. Okay, let's check the other one. What is the direction of the electric field at the dot? Yeah, you can see here. In this dot, for the negative, it should be inward. And for the positive, it should be outward. But for the positive, it is further. So which means this one is smaller. So the total will be to the like a negative. So which means the B should be the right answer. Yeah, the B is the right answer. Okay, let's continue to talk about electrical field of multiple charges. Yeah, for an electrical dipole, we can find the electrical field at any point by a vector addition of the fields of the two charges. You can see here there is a dipole electrical field at this point is in the position y direction. Do you know why? Because this one this direction, this one in this direction. Yeah, but this one is bigger, so which means the direction is positive y direction. For this point, for this dot, the dipole electrical field at this point is, yeah, for this here it is just in this direction and in this direction. So the total, yeah, the vector sum will be the negative y direction. Does that make sense to you? Okay, we can find the electrical field created by a dipole at many points to end up with a field diagram of the dipole. Yeah, in general, the field points away from the positive charge and toward the negative charge. Yeah, we know that. Yeah, like away from the positive charge, but the toward to the negative charge. Yeah, like we can find the electric field created by a dipole at many points to end up with a field diagram of the dipole. Okay, let's try to check one example problem. Actually, I think this one will not difficult to you. Yeah, you can see. Determine the magnitude and the direction of the electrical field at the point A. This one. Actually, you can see for this one, it will be away, and for this one, it also will be away, and for this one, it is like it will be toward. Yeah. So what you just need to calculate every electrical field using this equation KQ R. Yeah, you can and then for this one and this one you don't need to yeah, then like sum all those vectors and get the final like final magnitude and direction. You can see here for this one, and you just for this vector, you just like have the x component and y component. You can use this one, and then this one much smaller than this one. So you have the this direction and also this direction. You will choose which one is, and then get the final like magnitude and direction. Yeah, this is I just give you the hint. You need to resolve this problem by yourself, but it's very easy. Just like using this equation to calculate every like electrical field, and then do the vector sum. That makes sense to you? Okay, let's talk about uniform electric fields. A parallel plate capacitor is the arrangement of two electrodes closely spaced and charged equally but oppositely. You can see here there is a capacitor, and in this plate, in the upper plate, it has all the negative charge, and in the down plate it has all like the positive charge. An electrode is a conducting plate. Yeah, you can see the plates are widely compared to the distance between them. There is a distance between those two plates, and this cross, you can see this cross section view showing a small range near the center of the plate, far from the edges. Because the opposite charge is attracted, the charges are on the inner surface of the plates. Yeah. And inside yeah, this is this is inside the parallel plate capacitor. The horizontal components of the individual fields cancelled. You can see, and this direction component will be cancelled, and the vertical components add to given electrical field vector pointing from the positive plate to the negative plate. Yeah, you will see it will from, yeah, like this. Okay, yeah. Inside a parallel plate capacitor, the electrical field at every point is the same in both strength and direction. You can see in every point it has a same strength and like direction, yeah, for the electrical field. This is called a uniform electrical field. Yeah, we call this situation a uniform electrical field. And this equation introduces a new constant. Yeah, this is the like electric field in a parallel plate capacitor, plate area A and charge Q. And you can see this is the area, plate area, and this is the charge Q. Yeah, like this is the electrical field from positive to negative, how to calculate it. And this equation introduces a new constant. This one, we pronounce the epsilon zero or epsilon like tau, called the permittivity constant. We call this permittivity constant. Its value is related to the electrostatic constant, yeah, K. Yeah, we know K like before, and then this one is related to this one, and we can calculate this one. Yeah, this is a constant, which means this value is fixed. And there are a few things to note about a parallel plate capacitor. The field depends on the charge to air ratio Q divided A. Yeah, if you observe it. Yeah, Q divided A. A is the plate area and the Q is charge. Yeah, the field depends on the charge to area ratio Q divided A, which is often called the charge density. If the charges are packed more closely, the fields will be larger. Yeah. And our analysis requires the separation of the plates to be small compared to their area. If this is true, the space between the plates does not affect the electric field, and this spacing does not appear in the equation. Like this one, like the separation of the plates to be small compared to this area. Yeah, so which means this this distance will not affect the value for the electrical field. Yeah, like this. Yeah, this distance will not affect if you according to this equation. And you can see there is no d there. Am I right? So the shape of the electrodes, circular or square or any other space, is not relevant as long as the electrodes are close together. Yeah, if the electrodes are close together, and the shape will like doesn't matter. Yeah, not relative. Okay, yeah, let's talk about one example. Finding the field in an air cleaner. Yeah, long highway tunnels must have air cleaners to remove dust and soot coming from passing cars and trucks. In one type, known as an electrostatic precipitator, air passes between two oppositely charged metal plates, as in this figure. Yeah, the large electric field between the plates ions these dust and soot particles, which then feel a force due to the field. This force causes the charged particles to move toward and stick to one or the other plate, moving them from the air. A typical unit has dimensions and charges as shown in the figure. What is the plastic? What is the electric field between the plates? Actually, yes, there are so many like background, so much talk about the background, but the main question is just like ask you what is the electrical field between those two planes, and yeah, you can use definitely you can use these equations to calculate it. Yeah, and then yeah, because the space between the plates is much smaller than this area. Yeah, you can see the tunnel will be very big. Yeah, we will treat this as a parallel plate capacitor with a uniform electrical field between the plates. So then we will use the equation we talk about. We can find the field using equation 20.7. The area of the plates is this one. Yeah, one is the long. Yeah, one is this edge, and the other is this edge, and the area will be those two multiple together, and this is the area for that plate. And the field direction is from the positive to negative. Yeah, we know that from positive to negative, which means, yeah, it should be just like this, yeah. And which is to the left. Yeah, the field strength between the plate is, yeah, we use this equation. Yeah, E equal Q divide ellipse multiple A. Yeah, we know the Q equal what? Yeah, it has already, yeah, it has already give you here. Yeah, does it make sense to you? Yeah, this one. And then the constant, yeah, we know that. And the area we have already calculated. So we can calculate the final field, electric field. You can see, yeah, the question asks for the electric field, a vector, not just for the field strength. The electrical field between the plate is this one. So just pay attention. If what is the question asked here is just here is asking you the electrical field. It's not like just the electrical field magnitude. So pay attention to that. So you need to point out the direction. Yeah. And you can see the table 22 shows that a field nova, this one will create a spark in air. The field we calculate between the plate is just a bit smaller than this. Yeah, which makes sense, but it's a little dangerous. So you just pay attention to now, like make this electrical field like to this one. Otherwise, it will be dangerous. The field should be large, but not large enough to make a spark jump between the plates. Okay, let's continue. Let's talk about the electric field lengths. Yeah, electrical field lengths are imaginary lines drawn through a region of space to help visualize the electrical field. Actually, the electrical field length like does not exist in the real world. You cannot see it. For example, our Earth, yeah, there is electrical field, but you cannot see the electric field length. Yeah, because they are not existing. Yeah, we just like draw it like to help us to understand the electric field. Does it make sense to you? Yeah, the electrical field lines are drawn so that the tangent to a field line at any point, the tangent to at any point is in the direction of the electric field at, at the point, and the field lines are closer together where the electrical field strength is greater. If we know what the field vector look like, we can extrapolate to the field length. Okay, you can see this is a typical like electrical field length. Yeah, the electrical field length like represent the relationship between field vectors and the field. This is yeah, this diagram like shows the relationship between field vectors and the field length. You can see the electrical field vector. Yeah, this is electrical field vector is tangent to the electrical field line. Yeah, it's tangent. Yeah, it's tangent. It's tangent. Does it make sense to you? Yeah, the electrical field is stronger where the electrical field vectors are longer and where the electrical field lengths are close together, which means it's close together, which means the electric field is stronger. Yeah, does it make sense to you? Okay. Yeah, this is a field length of a positive point charge. It's just a one for one like a positive point. What is the field length? Yeah, we have already talked about this before. Yeah, the field is directed away from the positive charge, so the field lengths are directly radially outward. You can see outward. The field lengths are closest together near the charge, which means here has a stronger electric field. Yeah, that makes sense to you? Okay. Yeah, this is the electrical field length in an ideal capacitor. The field vectors are directed from the positive to negative plane. So the field length as well. You can see there is no like some place is closed, some place is loose, which means it is uniform. Yeah, the field is constant, so the field lengths are evenly spaced. Yeah. Okay. Field lengths cannot cross. You can just remember. Yeah, the field length cannot cross. The tangent to the field length is electrical field vector. Yeah, we talk about that, which indicates the direction of the force on a positive charge. The force must be in a unique, well-defined direction. So two field lengths cannot cross. Yeah, the electrical field is created by charges. Field lengths start on positive charge and end on a negative charge. Yeah. Okay, you can use the above information as a basis of a technique for sketching a field length picture for an arrangement of charges. Yeah, draw field length starting on positive charge. Yeah, you can see starting from positive charge and moving toward negative charges. Draw the field length so that the field vectors are tangent. You can see the field length, like a vector. It's always tangent, 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 tangent. That makes sense to you? Yeah. And to the field length at each point. Make the lengths closer together where the field, you can see here, the field is stronger. So you just make the lengths close together. And uh, where the field is strong, far apart, yeah, you can say far apart where the field is weak. Okay. Let's talk about one example, 20.10, drawing field length between a charged disk and a charged ring. Yeah, the figure shows a disk with a negative charge in the center. Yeah, there is a center negative, and draw and that has an equal amount of positive charge here. Yeah, draw the field length in the region between the disk and the ring. We will draw each field length by starting on a positive charge and moving in the direction of the field that a positive charge would feel. That is in the direction of the field. Yeah. Yeah, the you can see here this is yeah, because the electrical field should like outward from positive to inward to the negative. The arrangement of charges has a symmetry that makes the drawing straightforward. The field lengths go radially inward, each ending on a negative charge as in the figure. Yeah, this one is just like, yeah. The field length does not cross and they are close together near the disk. Yeah, close here. Yeah, maybe, yeah, here. If you draw more, yeah, which makes sense. The charges on the disk are packed more close than the charges on the ring, so we expect the field to be stronger near the disk. Our final picture seems reasonable. Does that make sense to you? Okay, let's talk about the synthesis 21, like just two key electric fields. These are two very important keys for electric fields. Yeah, the electric fields due to a point charge. You can see here we want to know the electric field E at a point P, located a distance r from a point charge Q. This is Q. Oh, sorry. Yeah, this is just a summarize for what we have already talked about. Yeah, and this is Q. And the E points away from a positive charge and toward a negative charge. And this is an equation for magnitude of electric field. Yeah, this is the electrostatic constant. Yeah, we know that. And this is magnitude of charge Q. This charge source charge. And this is the distance from charge to point P, yeah, R. So yeah, this is the electrical field due to a point charge. And this is electric field inside a parallel plate capacitor. Yeah, we talk about that. And the charge field points from the positive to the negative plate, and the charge Q is evenly spread out on the positive plate. The field lines are evenly spaced, indicating a uniform electrical field. Yeah, charge Q, negative Q is evenly spread out the negative plate. Yeah. So this is the equation for the magnitude of electrical field for a parallel plate capacitor. Yeah, this is here. This is a permittivity constant. Yeah, we know it is equal this one, and this is the magnitude of charge on each plate. Actually, those plate the charge negative and positive is equal, and this is the area of each plate. Yeah, actually, this area of each plate is also equal with each other. Okay, let's view some quick check questions. Yeah, two parallel plates have charge of equal magnitude but opposite sign. What charge would be made to increase the field strength between the plates? Yeah, A, increase the magnitude of charge on both, decrease in yeah, what change would be made to increase? Okay, increase magnitude of charge and decrease. Yeah, firstly, let's to write about the electrical field equation equal K, now K, Q, like this A, yeah. So the first one is just increase. So which means it will increase the field strength. The decrease, it will decrease. So this one is not right. And increase the distance. Actually, the distance is not related to the electric field. We talk about that. So it is not right. Decrease distance, no, it's not right because it's not related. Increase the area of the plate, which means this increase, which means the electric field will decrease. So if we want to increase, the right answer to A. Does it make sense to you? Yeah. Okay. Yeah, A. Let's talk about this one. The two plates, a parallel plate capacitor have charge, positive Q and negative Q plates on them, leading to a uniform electrical field between the plates. The distance between the plates is then doubled. Then the electrical field will be, yeah, actually we talk about that. The distance will not affect the electric field. So it will remain the same. Does it make sense to you? Yeah. Okay, let's talk about this one. A set of electric field length is directed as shown, at which of the noted points is the magnitude of the field the greatest. Yeah, we talk about that. The close, if the electrical field length closer and the like a magnitude of field will be greater. Does it make sense to you? So the answer is obvious. A. Am I right? Okay. Let's talk about this one. Two protons, A and B, are in an electric field. I think it's just miss a little here. Yeah, electrical field. Which proton has a larger acceleration? I think this one is yeah, like the largest acceleration, which means like has a larger force, which means has a larger electrical field. Where has a larger greater electrical field? I think A. Am I right? It's obvious. So yeah, like a stronger field where like a Fred lengths are closer together. Here you can see weaker field where the field lengths are farther apart. Okay, let's talk about the electric field of the heart. Yeah, actually this is an application. Yeah, a cell membrane is an isolator that encloses a conducting fluid and is surrounded by conducting fluid. While resting, the membrane is polarized with positive charges on the outside of the cell. When a nerve or muscle cell is stimulated, the cell depolarizes. When the charge balance is later restored, the cell repolarizes. Yeah, this is some like interesting thing about our human body thing. Yeah, the surface of the heart is positive on one side of the boundary between tissue that is polarized and tissue that is not yet depolarized, negative on the other. You can see here there is a positive side, there is a negative side. Yeah. And the heart is a large electric dipole. The orientation and strength of the dipole change during each beat of the heart. Yeah, this image is the electrical dipole of the heart. Yeah, here there is a cross section of the heart showing muscle tissue. Here there is a depolarized tissue, and this lens separates cells that has depolarized and those that have not yet tissue not yet depolarized. Then the charge separation at the line between the two regions creates an electric dipole. You can see here is a negative here, positive here is a negative, then creates an electrical dipole. The dipole, electrical dipole. The dipole electrical field generated by the heart extends throughout the torso. Yeah. And an electrocardiogram measures the changing field of the heart as it beats. The measurements can be used to diagnose the operation of the heart. You can see here, this is the field of the heart in the body. Yeah, the heart's dipole, here is a positive, here is negative, extends throughout the torso. Yeah, and then electrical cardiogram mirrors the changing field of the heart as it beats. Yeah, the measurements can be used to diagnose the operation of the heart. Amazing, I'm right? Yeah. Okay, let's check some like quick questions. Let's which of the following is the correct representation of the electrical field created by two positive charges? You can see positive charges, which means the electrical field will be outward, not inward. But here will be, here is inward, so this one is not right. Yeah, here is also inward, not right. Yeah, this one is our, but this one is inward, so it's not right. So the right answer must be C. Does it make sense to you? Yeah. Okay, let's talk about the other one. An electron is in the plane that bisect a dipole. What is the direction of the electrical force on the electron? Yeah, just pay attention. Yeah, this question asks you direction of the electrical force, not electrical field. Yeah, so let's talk about that. Yeah, here you can see, this one. This is like a electrical field length we draw. Yeah, and here you can see in this point, it just the electric field is just like this. Am I right? Yeah. So, but here because this is a negative electron, so it is a negative charge. So, which means it will be opposite. The direction will be opposite the electrical field. So the right answer should be A. Yeah, because you can see here the electrical field direction is down, and the electrical force should opposite. Yeah, it should be A. Does it make sense to you? Okay, let's talk about the other one, the other example problem. Yeah, I will just give you the hint for example problem. You need to like resolve it by yourself later. And if you have questions, just ask me, and I will help you to resolve it. Does it make sense to you? Okay, let's talk about this one. What are the strengths and the direction of the electrical field as the position indicated by the dot? Yeah, this dot. And specify the direction as an angle above or below horizontal. Yeah, actually, yeah, because you can see here, there is a positive charge source. There is a negative charge source. So which means it is for this dot, it will have this will have this direction field, and for this negative source, and will have this, yeah, because it will inward, so it will have this direction, and then you just calculate because it has given you the like a charge and the distance. You can calculate the distance from here to here, yeah, and then you can calculate the E equal what? K divide R square, and use this equation to calculate two different field equation, and then use some vector to calculate it. Does that make sense to you? Okay, let's talk about talk about the other topic called conductors and electric fields. Yeah, in a conductor in electrostatic equilibrium, none of the charges are moving. Yeah, you can see the electrical field inside the conductor is zero. And the charges in a conductor are free to move. If there is an electrical field, they will move, and the conductor could not be in electrostatic equilibrium. Therefore, the electrical field is zero at all points inside a conductor in electrostatic equilibrium. Yeah, you can see this one is just like in a electrostatic equilibrium. The electric field is zero at all points inside a conductor. Yeah, this is just some definition, some like yeah, some observation, like after many labs or experiments. Any excess charge inside a conductor must lie at its surface. You can see any excess like a charge inside a conductor must lie at this surface. Any charge on the interior would create an electrical field there. Yeah, here you can create an electrical field, but inside, yeah, the electrical field is zero. Yeah, it will reach to an electrostatic equilibrium. Yeah, and yeah, any charge on interior would create an electric field there, in violation of our conclusion that the field inside is zero. Am I right? Yeah. Physically, the repulsive forces of the charges cause them to move as far apart as possible without leaving the conductor. Yeah, which means, yeah, the electrical field at the surface is perpendicular to the surface usually. Yeah. Okay, the electric field right at the surface of a charged conductor is perpendicular to the surface. If the electrical field had a component tangent to the surface, it would exert a force on charges at the surface and cause them to move along the surface, violating the assumption that all charges are at rest. Yeah, you can see, even there is a electrical field at the surface, but this electrical field surface is perpendicular to the surface, not a tangent. If it's tangent, it will like violate the assumption that all charges are at rest. But if it is perpendicular, it will not, because it is perpendicular, which means the force, it will not like go outside. Yeah. Okay, let's check some conceptual example. 20.11, drawing electrical field length for a charged sphere and a plate. Yeah, this figure shows a positively charged metal sphere above a conducting plate with a negative charge. Stretches the electrical field and the field length. I think this one is now difficult to you, am I right? Yeah, you can see field lengths start on positive charges and end on the negative charges. Thus, we draw the field length from the positive sphere to the negative plate. Yeah, perpendicular to both surfaces. As shown in the like a figure, near the surface, the field is mostly determined by the presence of sphere, and the field lengths will be similar to those from a point charge. Yeah, you can see this is like similar to those from a point charge. Yeah, these are the conductors in electrostatic equilibrium. So the field is perpendicular to the surface. Yeah, perpendicular. Does it make sense to you? Yeah. Yeah, near the plant, the field is mostly determined by the presence of the plate, and the field length will be similar to those near one plate of the parallel plate capacitor. As we draw the field length from sphere to the plate, we draw them to smoothly transition between two cases. Yeah. And okay, let's continue to talk about conductors and electric fields. The electrical fields within a conductor enclosure is zero. Yeah, a conducting box can be used to exclude electrical fields from a region of space. This is called a screen. Yeah, metal walls are ideal for screen, but wire screens or wire mesh can be used. Yeah, okay. Yeah, although many excess charge of conductor will be found on the surface, it may not be uniformly distributed. At sharp points, the density of the charge is higher, and therefore the electrical field is strong. Yeah, about the conductors and the electrical fields, you can see some like videos to understand more. But this is just like some physical phenomena. Yeah, you just need to know about that. Okay, and the electrical field near very sharp points may be strong enough to, yeah, you can see here at the sharp point, the density of the charge is higher, and therefore the electrical field is stronger. Yeah, it makes sense, am I right? Yeah, the electrical field near very sharp points may be strong enough to uh, ionize the air around it. A lightning rod has a sharp point, so that if a building is beginning to accumulate charge, meaning a lightning strike might be imminent, a large field develops at the tip of the rod. Once the field ionizes the air, excess like a charge from the building can dissipate into the air, reducing the electric field and the likelihood of a lightning strike. Yeah, the lightning rod is extended to prevent a lightning strike. That's the reason why for some buildings there is a lightning rod. This lightning rod is tend to prevent a lightning strike. Yeah, this is the why this lightning rod can be used to prevent a lightning strike. Yeah, because the electrical field near very sharp point may be strong enough to aerolize the air around it. Yeah, a lateral has a sharp point, so that if the building began to accumulate charge, meaning a lightning strike might be, a large field develops at the tip of the road. Once the field aerosolizes the air, excess charge from the building can disappear into the air, reducing, yeah, which means the excess charge will go into the air, not just to the building. Does that make sense to you? Okay. Let's continue to talk about the forces and the torques in electric fields. And we define the electric field in terms of the force on a charge. Yeah. Yeah, in practice, we often want to turn the definition around to find the force exerted on a charge in a known electric field. The forces exerted on a charge is known electric field is, yeah, this one is, yeah, the force on a positive charge is in the direction of E. of E. Yeah, this is this is the force. Yeah, on a positive charge is in the direction of E. Yeah, this is force on a negative charge is opposite E. Yeah, this is the equation for the force exerted on a charge in a known electric field. Yeah, this is the electric field. This is a charge Q. Yeah, and yeah, under normal circumstances. Yeah, let's check let's check one example. Yeah, to finding the force on an electron in the atmosphere. Under normal circumstances, the Earth's electric field outdoors near ground level is uniform, about 100 N per C, directed down. What is electrical force on a free electron in the atmosphere? What acceleration does this force cause? Okay, yeah, we just need to use this equation here. Yeah, this is the electric field is uniform. The force is in the direction opposite the field, yeah, because it is an electron. And then the electric field is uniform as shown in the field diagram in the figure. Whatever the position of the electron, it experiences the same field. Because the electron is negative, the force on it is opposite the field. Yeah, we actually we talk about this in one question. Yeah. Okay. So let's just using this equation. Yeah, this equation to calculate the force. Q divided Q. Yeah, because it is an electron, so it will be the charge will be E, and this is the like electric field. Yeah, so this is the force we calculated. Thus, the force on this electron is this one and upward. Yeah, the electron will accelerate upward in the direction of the force. The magnitude of the acceleration is this one. It should be F divided mass. Yeah, and then this is the acceleration of the magnitude of the acceleration. Does it make sense to you? Okay, you can see the electric force completely dwarfs the weight force, even for this modest field. This implies a very large acceleration. We expected the electric force to dominate, so this makes sense. Yeah, that makes sense to you. Okay, let's check some example problem. Yeah, what is the magnitude and direction of the electrical force on charge A? Yeah, you can see this is charge A and this is B, C. So, any ideas? Yeah, actually you can see, yeah, the force, you can easily calculate the electric field, am I right? Equal what? Equal K Q R. Yeah, you can calculate this electric field because you know the Q, you know the R. Also calculate this electric field, and then you use this equation to calculate the force QE, because you know the Q and you know the E. Am I right? So then you can calculate the force and you know the direction. Yeah, for this one, this direction it will be like this one, and this direction will be this one. So, but this you can like calculate the you can decide the direction by like which one is greater, which one is like smaller. Yeah, yeah. I just give you a hint. You can calculate by yourself. Okay, let's do some check here. Yeah, a proton is moving to the right in a vertical electrical field. A very short time later, the proton's velocity is which one? So which means this is electrical field, and this is negative. So which means there is a acceleration to this direction, which means after a short time, it should be go to, yeah, because a very short time, so it will not move too much on too much. It just goes to this direction. Doesn't make sense because the original direction is here. Yeah, so it should be C. That makes sense to you? Yeah. Okay. Which electrical field is responsible for the proton's trajectory? Firstly, the electrical field should be uniform and not cross. Yeah, so which means we need to choose it from A, C, D. And because because trajectory is this one. It's just like similar with this thing, but change a direction. So which means it will the electric field should this direction. Yeah. So the right answer should C. That makes sense to you. Okay. Yeah. Let's talk about continue to talk about forces and torques in an electric field. Yeah. To get the colored lens produced by gel electrophoresis of a sample of DNA. You put the sample of DNA into a solution, then cut the DNA into fragments by enzymes. In the solution, the fragments, yeah, actually this is one application. In the solution, the fragments have a negative charge. You can see here, yeah, sample, yeah, it is negative charge. Drops of the solution like are placed in wells at one end of the container of gel. And yeah, electrodes at the opposite end of the container of gel produce an electric field that exerts an electric force on the DNA fragments. Drag forces cause some fragments of different size to migrate at different rates. Yeah, you can see different fragments have different size and so migrate at different rates. Yeah, and after time, the fragments sort into distinct lengths, creating a genetic fingerprint. Yeah, and two identical DNA samples, yeah, would produce the same fragments and therefore the same pattern. It is extremely unlikely that two related DNA samples would produce the same pattern. Yeah, so yeah, so like this example is just like yeah, you can help you this like a capacitor, like a uniform electrical field can help you to this to tell two different DNA samples is same or not. Yeah, yeah, like as you like view these things, what do you will think about? You will think this can be used to tell if this son is his father's son. Does it make sense to you? Okay, yeah, we just use this techniques technology to do the DNA tell the DNA differences. Yeah, that makes sense to you. Okay. Yeah, let's continue to talk about the forces and torques in an electrical field. An electrical dipole in a uniform electrical field experiments no net force. Here you can see because the force on the positive and negative charge are equal in magnitude but opposite direction, there is no net force on the there is no net force on this dipole. Yeah, and there is a net torque on a dipole. Yeah, in a uniform electrical field, which causes it to rotate. Yeah, because the dipole they are there is no net force, but because they are it is put in a electrical fields, so which will cause it to rotate. The electric dipole moment is a vector pointing from the negative to the positive charged dipole. You can see from positive from negative to the positive charge of a dipole. Yeah, this is a dipole moment. Yeah, and the equilibrium position of a dipole in an electrical field is with the electrical dipole moment aligned with the field. Yeah, this is a equilibrium position for a dipole. Yeah, when the dipole lines up with the field, the latter torque is zero. Yeah, the dipole is in static equilibrium. We can see that the dipole moment tries to align itself with the field. Yeah, does it make sense to you? Okay, let's talk about some quick chat questions. Yeah, a dipole is held motionless in a uniform electrical field. When the dipole is released, which of the following decreases a subsequent motion? You can see when it removes, this dipole, in a has no net force, and but you can see, this is electrical field's direction. It already has the same direction with this one, so which means there is no like a torque. Yeah, there is no torque. Yeah, so the dipole remains motionless. That makes sense to you? Yeah. Yeah, because this direction and this direction is the same thing. Okay, let's talk about that one. Yeah, the dipole is held motionless in a uniform electrical field. When the dipole is released, which of the following decreases the subsequent motion? Yeah, actually you can see because the electrical field in this direction, so this one will be move. Yeah, this dipole will be moved, and you can see, and it should like the positive should and the negative should be behind the positive should be, so it will be counterclockwise. Yeah, because you can see it will go to the negative, so the positive should be to this direction, negative should be this direction. Yeah, that makes sense to you. So it should be D. Yeah, and let's see the other one. A dipole is held motionless in a uniform field when the dipole is released. Which of the following this one? Actually, this one is just similar with this one, but the here is a positive, here is a negative, but this one is here is a positive, here is negative. So which means the positive will go to this direction and negative go to this direction, which means it will clockwise. Yeah, so which means it is C. That makes sense to you? Okay, let's talk about the other one. Which dipole experiences no net force in the electric field? Actually, we talk about that. If it is the dipole, it always there are always no net force. So all three dipoles, but just some have the torques. Some there are torques. But there is no torques, but there has torques. Yeah. So which means all three dipoles experience no net force. Okay, and which dipole experience no net torque in the electrical field? Yeah, because you need to make it the direction should the same thing. So which means this one there is no torque. Yeah, C is the right answer. Yeah, that makes sense to you. Okay, let's talk about the one example problem. I also give you some hints like some suggestion, and you need to resolve this problem by yourself. Okay, yeah, you can see an electrical field, and this electrical field that has given you the direction and the magnitude, which means this is the like electric field cause 2 gram ball to hang at an angle. What is the seat? This seat, because this charge, and this charge has this value charge, and what is which means you can use this equation to calculate the force firstly. Yeah, let's try to yeah, try to, yeah, you can use this equation. Hmm? Oh, you use this equation to calculate the force. Yeah, force is equal, yeah, sorry. Yeah, force is equal EQ. Yeah, EQ. Is it true? Let me try to double check. Yeah, it's sorry, it's QE. Yeah, it's a similar thing, but just the opposite to the direction. Yeah, and then you know the Q here, and you know the E here, and then you know the you know the force, and here you can see it has like a gravitated force, and also this one is the electrical field direction, and this is positive, which means the like force should be in this direction, and then you know this force, and you know the gravity, and you know this force. Am I right? So then you will know the angle. Yeah, you know this one and you know this one, you will know the angle. Does it make sense to you? Okay. And the next, this is what we talk about in this class. Yeah, we mainly focus on the electrical fields. Yeah, and how to calculate the electrical fields, how to represent the electrical fields, how to use the electrical fields length to represent the electrical field. Yeah, and some electrical forces based on the electrical fields. Yeah, and this is what we talk about in this class. And okay, let's do a summary. Yeah, you also can watch a video to find more interesting things. Yeah, I will not play it in here. Okay, firstly, there are some general principles. Yeah, charge. Yeah, we talked about this in last class. Yeah, there are two kinds of charges called positive and negative. Yeah, atoms consider a nucleus containing positively charged protons surrounded by a cloud of negatively charged electrons. Yeah, this is protons, and this is electrons. The fundamental charge E is the magnitude of the charge on an electron or proton. Yeah, this is the value for the magnitude of the charge. Yeah, for the proton, it will E. For the electron, it will negative E. Yeah, matter with equal amounts of positive and negative charge is neutral. Yeah, if most objects, yeah, is a neutral like status. Yeah, charge is conserved. It can be created or destroyed. Yeah, the charge cannot be created or destroyed. It just can be transferred from one object to the other one. Yeah. Okay. And next, we talk about the Coulomb's law. It's very important. Yeah, using this law, we can calculate the electrical force. Yeah, like between two different charge. Yeah, the forces between two charged particles Q1 and Q2 separated by distance are yeah, using these equations. And here K is a constant. We call it electrostatic constant. Yeah, it is this one or this one. You can use neither of these two. Yeah. Okay. And these forces are an actor or action or reaction pair directed along the line drawing the particles. The forces are repulsive for two like charges. Two like charges, which means one is positive, the other is positive, or one is negative, the other is negative. Attractive for two opposite charges. Opposite charge, one is positive, the other is negative. Yeah, the net force on a charge is the vector sum of the forces from all other charges. The unit of charge is a Coulomb. Yeah, C. Okay, and let's continue. Yeah, and in today's class, we talk about the electric field. Yeah, charges interact with each other via the electric field. charge A alters the space around it by creating an electric field. This is okay. I just the field is an agent that exerts a force on charge B. You can see this is a positive charge, and the alters the space around by creating a electric field, and then it exerts a force on charge B, and this is the equation for the like a electric force for charge B. If you know the electrical field, you know the charge for B, and then you know the force. Does it make sense to you? Okay. An electrical field is identified and measured in terms of the force on a probe charge Q. The unit of the charge field is this one. Actually, we didn't talk about this one, but I think it's easy to understand because the E equal what? E equal K, I think we talk about this one. E equal Q1, Q divide R. This one equal what? This one equal, like, this is prob Q. Which means E should equal like a K, Q, like a P, and a Q, and divide Q, so which means equal KP R. This is what we talked about at the beginning. And the electric field is a vector. The electric field from multiple charges is vector sum of the fields from the individual charges. It's similar to the force. And visualizing the electrical field. The electrical field exists at all point in space, but we cannot see it. It is invisible, but it exists. An electric field vector shows the field at only one point, the point at the tail of the vector. A field diagram shows the field of vectors at several points. This is for the positive, this is for the negative, and we use the electrical field lengths to represent the electrical field. The electrical field lengths are always parallel to the field vectors. Close where the field is strong, far apart where the field is weak. Go from positive to negative charges. And there are some applications. There are two types of material, insulators and conductors. Charge remains fixed on an insulator. Charge moves easily through conductors. Charge is transferred by contact between objects. A dipole has no net charge but has a field because the two charges are separated. A dipole will rotate to align with with an electrical field. We talk about the dipole will rotate to align the electrical field. Okay. There are some like important cases. The electric field of a point charge. We use this equation to calculate. We talk about this just now. And the electric field inside a parallel plate capacitor is uniform, and we use this equation to calculate. And here there is a constant, permittivity constant. Actually, this one is based on this electrostatic constant. And there are some like there is some conductors in electric fields. The electric field inside a conductor in electrostatic equilibrium is zero. Any excess charge is on the surface. The electric field is perpendicular to the surface. The density of charge and the electric field are highest near a pointed end. This is obvious, am I right? Okay. And this is what we learn in chapter 20, and we talk about charges, atoms, forces, and electrical fields. And electrical field, the relationship between electrical fields and electrical forces and how to represent it. Yeah. And I hope you guys can carefully finish the homework, the quizzes, and then you will know, like, you really understand what we have already talked about. Okay. Yeah, this is what we learn in this class. Okay. Thank you. Bye. See you.